for putting this together and inviting me. David Parks, I guess, I don't know how exciting this will be. I think Amin presented this paper in your lab on Friday. So I'm going to talk about seeding in networks when the information about the network is costly. And so I think this just maybe has some more general connections to thinking about what kind of information we should acquire, how valuable is that information for making decisions, what guarantees can we offer when we're not really going to have complete information of the process that we're going to intervene in. And so this is joint work with Hussein Elhanan and Amin Rayamayan. So the general setup is that we're interested in a problem in which we're trying to find the best K nodes in a social network to seed so as to maximize expected adoptions. What do we mean by seeding here? This might be that we imagine that we somehow have the power to target them with an intervention that will result in them adopting our product, right? And then our product adoption may spread through the network as they infect their neighbors with that behavior, right? I think this is already a little bit stylized in that often how we actually can intervene in networks is not so much by immediately making people be infected, but by offering them some kind of encouragement, right? By offering them some kind of nudge or inducement to adopt. But we're going to work with this stylized problem whereby we can select some seed set of people who are going to become infected or become adopters, and then that adoption will spread through some network. And so this problem is NP hard, but maybe if we assume some things about actually how this process is going to spread, there could be some nice greedy approximations. And so in particular, a lot of what we're going to look at is under an independent cascade model, this kind of SIR type model where each infected neighbor you have has some chance of infecting you once when they become infected. And it turns out that that kind of model of the cascade results in a global influence function, a function that maps from the seed set you select to the total number or set of adopters that is submodular. And so this is going to allow us to, if we observe the full network, use a greedy algorithm to get within this multiplicative factor of the optimal seed set. But generally, this assumes that we know this influence function. We know the process via which our product is going to spread in the network. And also that we know the whole network. Because how usually this is going to work is that we may repeatedly simulate from the network in order to compute what the adopter set would be from some initial seed set. And we're going to use that to as an input to our greedy algorithm. If we don't observe the network, how would we evaluate different seed sets? And I think it's really relevant to think about these cases where we don't really fully observe the network. In particular, there's a lot of interest right now in interventions in public health and development economics that aim to spread products in settings where we have maybe quite limited information about the network structure and it's quite costly to collect. So for example, Kim et al. Did an ambitious field experiment in which they're trying to examine methods for spreading the adoption of multivitamins and a water purification method in rural Honduras. And so they didn't really have a lot of prior information about the network structure of these villages. So they actually mapped that whole network structure by surveying everyone in the village. And this is quite costly. And in a lot of settings, the cost of measuring the network might really rival the cost of the rest of this intervention, right? So they measured all these networks, but actually part of what they did is contemplate avoiding conducting this costly survey by considering some seeding strategies that wouldn't require the network. So I don't know why they didn't consider actually some of the methods from the influence maximization literature. I know some of those authors are aware of them, but they were comparing random seeding, just uniform random seeding in these villages, max in-degree seeding, seeding the people who are named by the most other people in these networks. And then one strategy that's interesting in that it uses partial network information, what I call the one-hop seeding, or they call nomination seeding, in which you ask people who are your friends, and then you pick one of them at random. So that's a strategy that was proposed for vaccination and has been employed also for sensing as well, in addition to seeding. So the idea is if I want to select k nodes to seed, I'm going to sample k nodes at random and then select a random neighbor of each as the seed, right? So this only requires that I talk to k people. And it's going to hopefully exploit a version of the friendship paradox, whereby your friends have more friends than you do. And so we will have, on average, moved to more central vertices in the network. And then if we think that generally also higher degree nodes are going to be more influential, then this might be a good way of seeding. It might also not be. In fact, this method doesn't really pool the information we get from talking to these k different people, and it offers really no guarantees about the performance of the seed set we select. And in fact, it could go very poorly in some ways if it turns out that some of these higher degree nodes are actually all sort of connected to each other in the network, and so they're very redundant, right? And in fact, I would say there's really mixed evidence so far about the performance of this kind of one-hop seeding. So in some other work that I won't go into, we do some further empirical evaluation of these kinds of seeding strategies, and we're at least not finding overwhelming evidence in their favor. So one of the things that's interesting to think about with these kinds of seeding strategies that only make use of partial network information is that they're actually stochastic seeding strategies, or stochastic policies that map from the network, which maybe is only partially observed, to who gets assigned to be in the seed set. And so this actually allows you to do a lot of things like off-policy evaluation with these kinds of seeding strategies. So you can utilize data from field experiments that just do random seeding in order to evaluate these kind of seeding strategies. So if you're interested in that kind of more empirical take on the problem, we have another paper on that. But the general idea that I think is inspiring about this sort of one-hop seeding is to think maybe there's some ways of using the network, or partially observing the network, that could help us without incurring the cost of measuring the entire network. Okay. I think once you start thinking about the cost of measuring the network, you may even just say, why do we need to use the network at all? Perhaps just randomly seeding, or seeding based on other observable characteristics, might be sufficient. And so this is the argument in this recent paper by Akbakpour and colleagues, in which they suggest that network information is often just worth a few seeds more, right? So the idea being, what if I sort of denominate the cost of measuring the whole network in terms of my cost of seeding another person? Okay, how expensive would that have to be for me still to want to measure the network? And so in their analysis, and they're looking at an average case over a bunch of family of random graphs, they find that, okay, actually just adding a constant number of additional seeds to k and seeding those at random, so seeding this slightly larger seed set, that's going to outperform optimal seeding of a smaller seed set. So this is an argument that suggests maybe we'd be wasting our time measuring the network at all unless it's very cheap to do so, right? Now, it's worth noting that this is an average case result over a family of random graphs, and also that this is really limited to cases where things are pretty viral, right? Where things are actually going to spread quite a bit. And so we're actually going to result, there's going to be a large number of people who end up adopting, which, I mean, is every viral marketer's dream, but may or may not reflect reality. Yeah.
What do you mean by cascade sizes? Or
so with the cascade size being just the total number of adopters at the end. Yeah. So yeah. So how many people end up infected from this this spreading process? Okay. So part of what we're going to do is try to be inspired by both this kind of warning that maybe network information isn't always so valuable. Also, this idea that maybe we can adopt strategies that are just going to sample from the network to do something that could offer some of the kind of guarantees that appear in the influence maximization literature, but with only this kind of partial information. So the problem, as we're going to formulate it, is that we're going to work with this independent cascade model. So the idea here is that each edge has a one-time chance to pass adoptions with probability p, right? So when a vertex becomes infected, then it infects in the next time step each of its neighbors with probability p, and then it's done. It's no longer infectious. So if you're familiar more with the epidemiological literature, this is an SIR model with deterministic transitions from I to R. So you start out susceptible, you can become infected. Once you're infected, you only remain infected or infectious for one period before you recover or are removed. So one of the things that's interesting about this is you can actually think of this as just a process whereby we prune the graph, we sparsify the graph, keeping each directed version of an edge with probability p, and then we run a deterministic spreading process on that graph. Okay. And then we're going to try to choose the best k nodes to maximize the expected number of adopters. And we're going to specify that we really only have limited access to the network structure through queries of the graph. So we're going to think about how we might actually interact with this network in order to learn about it before making the seeding decision. Yeah?
Do you have a Bayesian perspective on where, on the network generation process, for example, or how the graph has been?
A model of the graph. So we're going to, all the results that we're going to show here are all worst case approximation results. You can think about then what happens if you have some beliefs about the model that the network is drawn from. I think things get a bit easier, and I'll mention briefly some work in which you posit a network model. Yeah. Part of the challenge in a lot of this, right, is that many of the models that we have of social networks don't fit any social networks particularly well, or don't necessarily have that much content. So really relying on the idea that the actual network is within, we can think of it as a draw from some random graph model, might mislead us in some various ways. I mean, actually even, that Akva paper I mentioned earlier, they consider a pretty large family of random graph models, but there's still some things about that set that is a bit restrictive. I think also we really wanted to, in this paper, be kind of in conversation with the influence maximization literature, which has focused so much on these kinds of worst case guarantees. And to say that really we can do something there. I think in terms of the empirical import, a lot of times you'd want to try this out on a lot of realistic empirical networks. And at the end of the talk, I'll show you some simulations of these methods on an empirical network. Okay. So yeah, if we do think that our network is drawn from some particular random graph model, that might help us a lot. So there's this very recent paper by Widler and colleagues that looks at what if the graph we have is drawn from a stochastic block model. In particular, a stochastic block model that has this kind of community structure where there's higher probability of edges within blocks than between. Then one of the ways we could think about the problem that we have in doing influence maximization is we want to make sure that we get seeds in each of the largest blocks. Right? There's a bunch of these different communities, and yeah, it might be possible, but perhaps improbable that the contagion is going to jump between communities. So it's really important that we seed each of the largest blocks. And so we can do that by taking a random sample of nodes, using some random walks to try to figure out, are we in large blocks here or in small blocks, right? And then try to seed the largest blocks uniformly at random. And so then this can offer some guarantees, but these are guarantees given that we have a network that's drawn from this particular random graph model. So I think this is like an interesting step in sort of the same direction that we're taking. We're going to focus on worst case guarantees, right? So what we do here is propose some polynomial time algorithms that have these almost type guarantees for general graphs using a bounded number of queries. And I'll describe to you how we imagine that we're going to be able to query the network. And then this gives us essentially a framework to quantify the value of network information, because by having these methods that allow us to bound the number of queries, we can think about how much do things improve as we query more, right? And at what point do we want to stop querying the network, right? So it gives us a framework for thinking about the value of information about a network that's not all or nothing, but that instead says, look, there might be kind of diminishing returns to learning more and more about the network. So we have some methods that will allow us to learn about the network and then, to some degree stop and then seed based on that knowledge. Okay. So the two query frameworks that we're going to work with we call spread queries and edge queries. And they're both pretty related in that we're going to do something like run the process of spreading on the network, possibly with some modifications. And so with the spread queries, we imagine that we can seed a random node and see the set of eventual adopters from seeding that random node. That is that we're kind of able to run restricted, some kind of restricted version of this exact spreading process that we'd like to learn about. And so you might think this could arise if, say, prior cascades are observed, right? So maybe we have a bunch of observational data, and we think perhaps this could tell us about the network. And we might also think that in some cases we could cheaply seed a different behavior. So maybe what we're actually trying to decide to do is, pick people to be, influencers who we're going to compensate in some other kind of way. But we could imagine that instead we can just do things like be seeding coupons or links that are low cost but are spreading via the same network. Then in the edge queries setup, we think about a case where we can talk to somebody and observe one of their neighbors at random, and then possibly repeat this so that we talk with somebody and then we talk with some of their friends, etc. Right? And this is often used in some prior algorithmic work. And I think in terms of application, this starts to look a lot like various snowball or RDS type sampling. RDS being respondent-driven sampling, something that's widely used to try to measure the size of hard-to-reach populations, for example, like intravenous drug users. I think both of these query frameworks, as we're going to present them, are a little bit stylized. And so as the person in this team who's actually the most of a social scientist, I'm definitely sensitive to the idea that these are a little bit stylized query methods. But I think they actually do have an interesting relationship to how people are really doing these kinds of surveys. So in the edge queries case, we think of it as observing a random neighbor of a vertex and kind of repeating this. You would imagine actually probably what you would do is once you talk with somebody, you might sample their whole ego net. You might ask them about a whole set of people. But usually we don't ask people for everyone they know. Often there's some kind of a cap. They're only going to tell us about 10 people. We only ask about 10 people, that kind of thing. So it's not so divorced from the actual kinds of processes we might use to measure networks here. Okay, so the thing that's common to these kinds of approaches is that rather than optimizing the influence function on the original graph, we're going to do so on a subgraph that's sampled in a particular way from the original graph. And it turns out that we're going to use sampling methods that have a kind of close relationship to the spreading process itself in order to end up with these kind of properly sampled subgraphs. Okay, so what does the sampling look like? So when we're considering the spread queries, the idea is that we're going to imagine seeding a particular vertex, and then we're going to observe the set of vertices that adopt, given that that vertex is seeded. And so here, we seeded this vertex, and then the contagion spread from there. And so the idea is actually in spread queries, we don't really need to observe the process via which it spreads at all. So we don't necessarily need to observe these edges. We're only going to just observe this resulting set of adopters. Okay, so each query sees a single node and outputs the identity of the resultant adopters. And then the main idea is to use the identity of the adopters from a number of these independent cascades to then seed k nodes with optimal approximation guarantees, right? And so what does this look like? We're going to repeat this multiple times. So here's one instance of doing the spread query. Then we pick another root node at random, and we run another spreading query, pick another root node at random, run another spreading query, right? So now we have, say, these 3 different spreading queries that we've run, okay? So how are we going to go about selecting our seed set? Yeah?
What are the rules of the spreading here?
So the rules of the spread are going to be the exact same as the rules of the spread of what we're actually trying to spread later. So this is going to be that this is an independent cascade model where when we seed this vertex here, then it spreads to each of its neighbors with probability p.
Right,
yeah.
right, you mentioned it. Sorry.
Yeah. And we do consider an extension to another related contagion model, but yeah, this is going to be this kind of simple contagion, epidemiological contagion process. Yeah.
So basically you're finding the marginals of your function, marginals of adding one element, right?
Right, so we are going to also, like the classic influence maximization work, you try to use a greedy algorithm here. And so you can think about how that's going to apply. Instead of applying this greedy algorithm to this full set of influence functions estimated using the full graph, often via Monte Carlo simulations. Instead, you can think about what we've just done as having this very limited number of Monte Carlo simulations that only involve seeding a single node, and that gives us access to a bunch of these cascades. So, so the idea is that the first node that we're going to pick in this greedy way is the one that appears in these cascades most often, right? So the idea is, okay, we seeded from here, and okay, if this, let's think about this node. It appears in this cascade, in this cascade, in this cascade. So if we're in an undirected graph, which is the setup here, we'll consider the extension to directed graphs in a second. So all the influence is symmetric. Then this is also telling us something about the cascade, the probability of a cascade going from here to this random node, right? So,
So can I ask a question?
yeah.
So there are some papers that are thinking about maximizing stochastics of modular functions.
Yes.
And then they don't assume having query access to the function. You have access to unbiased estimators of the gradient, which are all the marginals that you get at every set S.
Yeah.
And apparently you're kind of like doing the same thing. You fix the first
Yes.
one, then
Yeah. And in the paper, we're definitely drawing on a bunch of that work on sketching approaches to optimizing submodular functions, for sure. Yeah. Okay, so then given that we have this undirected spreading process, that's going to allow us to find the seed that would result in these random nodes adopting most often. Okay, then how do we greedily select the next member of the seed set? We would discard all cascades that are already covered by the seeds that we have selected, and just then look at the possible seed that appears in the most of the remaining cascades. Here we've constructed this so that, in fact, if we have selected the seed first, then all these cascades would be removed, right? So we would need more of these cascades in order to really be able to do anything smart in selecting the next seed for our seed set. Okay. Right? So this is just consistent with the idea that in this kind of independent cascade model, the main thing that you're trying to do in selecting this set is avoid redundancy, right? That you're just trying to avoid sampling seeds that are resulting in picking up the same set of adopters as others. Can you remind me, until when do I have this?
So now it's about 15 minutes.
Okay, great. Okay, so one of our first results here is an approximation guarantee for these spreading queries. And so we can then get within this this bound on a loss compared with the optimal seeding. And so one of the things you might be, disappointed about here is that we have this loss that's this epsilon n factor. And so you might wonder, a lot of the other kind of approximation results for these sort of submodular functions don't have this kind of factor, right? That it's just we have some constant multiplicative factor off of the optimum. But it turns out that it's impossible to avoid that. And so in these spreading queries, it's really impossible to, if we're considering this worst case scenarios, there are graphs where we're going to incur that kind of a loss. So here's one of these worst case graphs. So you imagine that our graph consists of a whole bunch of isolates and then also a clique. So we're going to need to have a lot of these spreading queries before we hit the clique. And so in this worst case, we just miss this clique entirely. Now, to me, as someone who cares about empirical networks, it's kind of encouraging that a lot of our really worst case results here are networks that don't look anything like real networks. So that's that's kind of nice. But I think we have to consider those kind of scenarios. Okay. So so that's one of the families of results, is looking at these just running these spreading processes from seed sets of size 1. Which could come from historical data or from the ability to seed things that are a bit cheaper than what we're trying to seed. Yeah.
So do you have any results for graphs drawn from like a stochastic block model, for example? And I guess that kind of relates to Rod's question, because these papers that do it there use seed sets of, like they use spreading queries on seed sets of size larger than 1.
Right, right. Yes, you mean as an input? Yeah. No, we don't have any results on the stochastic block models. I think we're going to run some simulations with that, just actually for comparison with your paper. So I think, to me, I have trouble getting excited about standard versions of the stochastic block model. Just is not clear that it looks that much like a lot of the networks we're encountering, or a lot of the networks that might be relatively hard cases here that are not like this, but that are potentially hard cases. As we'll see, actually, for some of the other query methods that we consider, there's some different hard cases. Yeah, I mean, I guess something like maybe a degree-corrected stochastic block model gets a little bit closer. But also, usually stochastic block models don't have enough triangles in them. So I don't know.
It just seems easy to kill this linear factor. If
Yes.
Any kind of distributional assumption on the graph model.
Yeah, yeah. Yeah, and I think that's one of the trade-offs in this. So this is, I don't, for those of you who maybe know some of my other work, I don't normally do like computer science style, like worst case approximation guarantees. So that's just sort of kind of where we ended up with this, is in some ways really wanting to be in conversation with the influence maximization literature and say that there's something you can do here even in the worst case. But yeah, I agree that this is not the graph that we're encountering in reality.
So your theorem you had on the previous slide, just trying to interpret what this kind of bound means that you've been talking about for a while.
Yeah.
So if op is not order n, is this bound not interesting?
Yeah, so yeah, I think that gets to this point of, okay, if we aren't in a regime where a lot of people end up infected, maybe this is a bound that's not particularly interesting. Yeah. Yeah, I think that's a good point. Yeah. Yeah, I think that's accurate. So I think that is a good point relative to what I said earlier about this aspect core result, right? That's all in this setting where we have an eventual size of the cascade that's order n. Yeah. Yeah, I think that's a good point about this, that maybe in some sense we're in that, we have that same problem, is that we're not really saying much unless things are order n. Yeah. Cool. Okay, so then the other kind of query model that we consider is this edge query model, where we're going to query a node and essentially ask that node to reveal its edges with probability p independently at random. So this is the same p from the contagion model. And then proceed to query its neighbors, etc. So you can see that this is also kind of a spreading process in the same way, but this will turn out to be different in a couple of nice ways. So one of the things with the seeding models, we're imagining that we pay some cost to seed something that's kind of this cheaper thing to seed, right? And then we observe the eventual adopting set, but it's not costing us anything as it's spreading, right? Whereas in this scenario, we're imagining we're going to have to pay a cost each time we sort of take a step along the network, because it's not that our coupon is diffusing, we're actually going around and surveying people, right? And so what we're going to try to do here also is bound the number of people that we end up talking to, right? So rather than thinking of the queries in terms of seeding these cheap coupons, we're going to instead really want to be limiting how many edges we query. And how I would actually think about this is that probably what we would do really is talk with somebody, learn a bunch about their EgoNet, and then sample some of their neighbors to talk to randomly. So we may observe a lot more edges, because if I think, just as a social scientist, like, okay, what is the actual set of costs that you face when you are doing this kind of surveying? It doesn't really cost that much more to have somebody reveal 10 of their neighbors than to have them reveal each of their neighbors with probability p. In fact, it's not quite clear how you get them to do that, but without them incurring the cost of thinking about all their network neighbors. So the idea is that then we're going to start from this random set of initial seeds. We obtain multiple subsampled copies of the original graph. And so this is going to look still a lot like the spreading queries, but there's some ways that this will play out differently when we get also to directed graphs, right? So here's what this edge query might look like, is that we start from these different points, and we are taking these steps, again, with this probability p, but we have multiple starting points here potentially, right? So this need not be a connected component, a single connected component. We repeat this again, and we repeat this again. The idea being that we're starting from these same points, but taking these different random walks. Okay. So the value of each connected component is then the number of initial nodes that are in this component. So again, we're going to think about, okay, if this seed, if this potential seed appears in this connected component, how valuable is it to capture this component? Well, it covers some random set of starting points. And given, again, that we're in this undirected setup, these are also ending points. These are eventual adopters. So if I started with this in my seed set, then this is telling me something about how likely it is that these 3 random vertices are going to go ahead and adopt eventually. Okay, and so then we're going to employ a similar kind of greedy approach, where the total value of this node is the sum of the value of its connected components in each of these cascades. And so again, we're going to go ahead and select this. Greedily select this node to be part of our seed set. And then as we repeat, we're going to remove all connected components that have already been covered by a previous seed. Right, so it's the same kind of greedy approach here. Okay, so then we also have an approximation guarantee here, where we're again going to incur this same kind of order n loss. One of the things that we get to do here is that we're going to be able to stop querying once a connected component becomes really large, right? So in the seed query, we're imagining that the spreading process just keeps continuing costlessly for us. Here, the spreading process, we're paying each time that we continue this spreading process, each time we continue this respondent-driven sampling-like process. And so we're going to want to really halt that process at some point if we're going to have any bound on how many people we query. And so once the connected component gets large enough, we can actually stop querying So why, again, do we need to have this order n loss here? Well, there's these cases like this that are these hard cases here. So we imagine you start with a network that consists of a bunch of k-clicks, and then you rewire some subset of the k-clicks so that they're connected in a ring to each other. So now they form a giant component. We'd really like to hit this giant component, but if we're engaged in this kind of edge querying process, we're not really going to discover these edges. We really have to find these edges in order to be able to distinguish this connected component from all these other smaller connected components. So again, it's somewhat encouraging that we think this isn't the kind of thing that normally happens, and this is the sort of worst case that occurs when you have P very large, when the contagion is spreading with high probability, right? Because actually I think in a lot of practical settings, the contagion may not really be spreading here with high probability. So I think this is also a case that's interesting related to the question about the stochastic block model, because this is actually something that looks kind of not that different from a stochastic block model, but part of it is that we've engineered this, that you're really keeping a certain number of edges here. So it's much more like a configuration model version of a stochastic block model. Because in a stochastic block model, sometimes these edges wouldn't exist, or sometimes there'd be more of them. And so I think that would make this problem easier. Yeah. Okay, so I think one of the big issues in thinking about how to spread something in a network is a lot of relationships are asymmetric, right? So I have a lot less influence on Oprah than she has on me. And so, so to me it seems like you really want to account for this asymmetry in this process. And so how could we actually account for handling a case where there's directed, possibly weighted graphs? And so everything we do pretty straightforwardly applies to a weighted graph. Now to apply it to a directed graph gets a little bit more complicated. So and this is actually where I think the edge queries really shine, because actually if you look at what people do in a lot of these surveys for public health, for education, for development economics, is that they ask people, like, who do you go to for advice about X, right? So we're trying to, say, in rural China, get people to adopt weather insurance. So we ask people, who do you discuss matters related to farming and personal, household finance with, right? And then that might be the set of people who are influencing you, right? Or who do you, turn to for advice about health? Is a similar survey question used in some studies in Uganda. So it seems like there we're actually essentially able to spread in the opposite direction that the contagion is eventually going to spread in, right? Because if you think about how everything that we've looked at so far works, is that we're using these random starting points and checking to see whether they would adopt if we had chosen a particular seed set, right? So it's really important that essentially we're able to run a spreading process kind of in the reverse direction that it's actually going to run later, right? But that's precisely what a lot of these surveys aim to do. They ask people these kinds of questions. And so that's why, for example, in that Kim et al. Study in Honduras, one of the strategies they consider is looking at people with high in-degree, people who are named by a lot of people, because those are typically people who are expected to be influential. So actually the edge queries approach essentially works more or less in the same way, right? That we just need to assume that we're running this process in the reverse direction. So we reveal each incoming edge with their associated probability. Now, of course, actually this is sort of reverse the meaning of incoming to go along with the contagion as opposed to the naming process. So that's actually nice, and I think that's one of the reasons why I, in imagining practical applications of this kind of approach, really like our edge query analysis, even if I think it's not the number of edge queries we have to make in order to get some of the approximation guarantees doesn't look as favorable as the spread queries, but I think it's actually a lot more practical. Spread queries, that doesn't really work out. I mean, basically, yes, you can imagine, oh, what if we can spread in the opposite direction? Okay, there's no way you can really imagine that you're going to be able to costlessly spread in the opposite direction. So if you can't, then you end up with situations like this where we have a star and you know, there's really no way for us to figure out that this would be the correct seed. So we can also extend this to some classic variations on the contagion model, including the linear threshold model. I don't really particularly find the linear threshold model interesting at all, but a bunch of our results will apply to that. Okay, so I'll just show you some brief empirical applications. So here we're looking at one of the largest network in the so-called Facebook 100. So these early snapshots of Facebook networks at universities. And so there's a lot of degree variation here, shown on the right. These are the nodes with the 100 nodes with the largest degree. So this is a pretty large network that then we're going to try running some of these queries on and see how we do. So essentially we can then look at how many queries do we run and what is the spread size that results from that, right? So if we run a ton of queries, basically we're just going to recover the standard greedy optimization approach here. If we were to run no queries, which we don't really include here, we have this random seeding result. Then we can consider this for different numbers of seeds. So for this case where we only have 2 seeds in yellow, we see that there's actually like pretty rapidly diminishing returns. We're able to run a small number of queries on this network, you know, like under 30 queries. And essentially we have the same performance we'd have if we run hundreds and hundreds of queries, right? With a larger seed set, this becomes a little bit different, right? And you can think about the logic of our spreading queries that we ran before. We're going to be dropping a lot of these queries, right? So in order to select the second element in the seed set, the second vertex to add to the seed set, we discard all the queries that are already covered by our first element, right? And so that results in there being continual gains to doing more and more queries. But we see that really, you know, we can actually, by you know, trading off between a smaller seed set size and a few more queries, we can potentially do better by using this kind of partial network information. So one way of thinking about all this practically is if we specify some ratio of costs for querying and some costs for seeding, what would be the optimum strategy here? So just as an example, let's think that each unit who adopts, we get this revenue of 0.01. Our cost per query is 0.1, and our cost per seed is 1. So it costs us 1/10 to query as to seed. So this would be, if we're sort of imagining spreading something that's much sort of cheaper to seed, it's 1/10 of the cost to seed than the thing we eventually want to seed. Then we see that there's going to be these kind of just interior optimums where, you know, it may make sense for us to go ahead and actually use a smaller number of seeds, so not go for this, you know, seed set of size 10, and to collect some network information, but not to collect an exhaustive amount of network information. So I think what I really like about this kind of way of thinking about this is it allows us to consider you know, some interior solution between collecting the full network information and just doing random seeding, right? And I think you know, we're continuing to do a lot of these kinds of simulations with empirical networks that there'll be kind of interesting results along these lines where a lot of times we want to rely on some network information but not all the information. So in conclusion, basically the idea is that we're using past spread data or a kind of iterative survey like RDS or snowball sampling to acquire some network information. Then this you know, allows us to think about a way of quantifying the value of network information that's beyond this all or nothing. And that accounts for the fact that a lot of times information about the network is going to have a lot of diminishing returns. So thanks a lot. It was really great working with my co-authors on this. Amin Rayamayan, who's a postdoc at MIT is on the job market this year and has also been doing some great work on contagion and networks as well. So thanks a lot. Yeah.
Your edge query, the way you formalized it, it was responding with probability, kind of,
Yeah.
I guess, associated with the probability. Do you
Yeah.
have any theory that, or do you have any theory to talk about what if I give you my top set, or, right? Because that probability is probably not realistic.
Yeah, that's something we've talked about a little bit, is what if instead we're able to query your top 10 by probability, right? If you imagine there's heterogeneous probabilities of me being infected by different people, and I can report to you the top 10. Yeah, I think there's various ways that can end up being hard to deal with. I think in practice that's probably a lot of what this looks like. So and that's some of the things that I would at least hope to continue to evaluate through empirical simulations, and maybe actually trying some of these techniques in field trials, or looking at contrasting actual adoption data with survey data. But yeah, I think it's not something we've tried to really say anything about formally.
So I have sort of a meta question, thinking
Yeah.
about this stream of research with survey research methods. So with
Yeah.
PSID, for instance, you are worried about getting a representative sample of households, and here you, it's almost like bridging the two types of research, but you're not thinking or considering representativeness is not a
Right.
consideration.
Yeah, well, one way of thinking about it, I guess we assume that somehow we can enter the network at random points, because it really is important in these kinds of queries that we've started from random points, right? Because that's how we're going to assess how much of the network we end up covering.
So the initial set of contacts are representative.
Right,
by
right.
assumption. Okay.
Yeah. Yeah. Yeah.
Maybe a follow-up on David's question. I'm referring to the Gossip paper. I don't know if you know the paper by Banerjee and Chandrasekhar.
Yeah.
So in many social applications, you know more actually. You know things which are not about your neighbors. You know about, I can identify whom I believe is central in the network.
Right.
So if the query was not about your neighbors, but about whom do you think is the most central, I don't know how you would fit it in
Right.
in an algorithm, but that
Yeah.
sounds like, in practical terms, it sounds very useful.
Yeah, I think so. So I thought about, so in that paper, one of the things they ask people is just like, oh, if I wanted to spread information about a concert or something like that in the village, who should I talk to, right? And so this relies on the idea that not only can I report like local information of who influences me directly, but who maybe indirectly influences me. So I think that's definitely an interesting angle. And in some of the other work I've done on this one-hop seeding, part of the question there is like what questions do you use to elicit the network? How ambitious do you want to be? Because I would describe that as a very ambitious question. I'm just like, hey, tell me who the seed set should be, right? And maybe people know that in some cases. Yeah, I think that's interesting. I imagine we could formalize that through looking at, if we really believe people, then that could be some information about just the fact that they are included in the eventual adopter set of that person. Yeah, that might be actually worth looking at a little bit more. That requires maybe these strong assumptions about the idea that people actually can report who influences them. And it's not so much that I'd be skeptical that I'm not influenced by these people that I report, but there may be other people who in fact are more indirectly influential on me. And I don't necessarily, they're not known to me. Yeah.
Great, thanks a lot. Let's have a coffee break.